Okay, hello everybody. So this is the second lecture that Professor Nesvorný, who is invited professor here at Collège de France, will give. So last week he spoke about the formation of binaries in the Kuiper belt. Today we remain in the outer solar system. So in this second lecture it will be about the history of comets from the protoplanetary disk to their current source reservoirs and their journey back from the source reservoirs to the orbits where we observe them. So, David, please.
Thank you. So, good morning. Thank you for coming. Today we will talk about the early evolution of the solar system. We will see how comet reservoirs form in the first place, and then how comets come back towards the sun, where they become active. So I will start with a few pictures. This is an example of a comet from this year. Comet Lemon shows the two characteristics that are famous for comets, which is the coma and the tail. Now the coma is composed of gas and small dust particles that are ejected from the comet nucleus. In the case of the Lemon comet, the coma is distinctively green, which is thought to be produced by the emission of C2 and Cn from the coma. Now the tail is mostly of very small dust particles that have been ejected from the comet nucleus, and now they are slowly drifting away from the nucleus. These structures are very large. The coma can be tens to hundreds of thousands of kilometers across, and the tail can be easily hundreds of thousands of kilometers to millions of kilometers. So these are very large structures compared to the comet nucleus. And they are clearly visible because of just the combined emission cross-section of the small dust particles and the molecules in the coma. Inside of each comet coma is a nucleus that's responsible for all the activity. And this is a beautiful image from the European Space Agency Rosetta mission of comet 67P Churyumov-Gerasimenko. As you can see, the nucleus of 67P has very interesting shape, and that's typical for the comets. They have very interesting shapes. This looks like maybe a contact binary that has been heavily eroded on the surface. And if you look at the surface, you can see clear signs of activity with slabs of volatiles removed from different parts of the nucleus. You don't see any craters on the surface, which is clearly a sign that the surface is very young, right? The old surfaces of asteroids are heavily cratered, or any surfaces are heavily cratered. So the fact that you don't see any craters means that the surface is very young. And you can actually see the activity, the ongoing activity in the background. All these jets of gas are produced at the terrains on the surface of the comet that's currently active, sublimating. The gas is ejected and carries small particles with them, and that, of course, connects to the coma, and then the small particles continue to the tail. This comet in particular has about 4 kilometers in size, so there is a very large range of scales involved in cometary activity. They start at kilometer scale and then go all the way to the tail, which may be millions of kilometers long. Now, as for the orbital classification of comets, comets have been traditionally classified into two categories. The one which have short orbital periods shorter than 200 years. A good example of this is comet 1P Halley, which has orbital period about 75 years. So every 75 years it comes close to the sun, becomes active, and then leaves. So basically these kind of comets are expected to be seen during civil perihelion passages over and over and over again. The long period comets, on the other hand, have very large orbital periods in excess of 200 years. And a good example of this is the giant comet Bernardinelli-Benstein, which is showing activity at 24 astronomical units from the Sun, probably because of the sublimation of CO2 ice or ammonia. This comet has orbital period of 4 million years. So that comet, once it leaves the inner solar system, we will not see it again. So that's the basic distinction between the short period and long period comets. Sometimes the long period comets are also called the near parabolic comets, to highlight the fact that they have very elongated orbits which are close to being parabolic. Eccentricity is close to 1. Another distinction between these two kind of comets is the inclination distribution. So orbital inclination is basically the tilt of the orbit with respect to the plane of the solar system. It turns out that the short period comets have very long orbital inclinations, so of the order of 10 degrees. So they stay very close to the ecliptic and follow the motion of the planets around the Sun. On the other hand, the long period or near parabolic orbits have very large orbital inclinations. In some cases, or in fact, in many cases, the inclinations are above 90 degrees, meaning that the comet revolves around the Sun in the opposite direction than the planets do. I will use color coding through this talk, that the long period comets will be blue, and the short period comets will be red. So to give you some sense how the orbits of the comets look like, this is an initial view from quite a distance. This block is 20,000 kilometers across, so you're really far from the Sun. And what you see is a sample of long periodic comets. And you can clearly see that they have very elongated orbits, and the orbits extend in all sorts of directions. They have very large inclinations. Now, we will zoom in to see the short periodic comets as well. So we are zooming in. These circles are the orbits of the giant planets, so Neptune, Uranus, Saturn, and soon we will see Jupiter in the inside. So as I said, the red orbits are those of short period comets. I have plugged the cometary orbits in an n-body integrator and show you how the comet orbits also evolve over time. As you can see, the cometary orbits overlap with the planetary orbits. So there is a potential for encounters. And in fact, these encounters are the main driver of orbital changes in comets. It happens that frequently a comet passes past Jupiter, feels the gravitational force of Jupiter, and the trajectory becomes deflected, and it evolves to a different orbit. So planetary encounters are important driver of orbital changes in comets. So, well, these are the short period comets which are in the solar system plane, and these are the long period or isotropic comets. Now it is always useful to look into orbital elements, because of that simplifies the insight we have. So what I've done here is that I plotted the orbits of cold comets in terms of the orbital period on the x-axis. Know that this is a logarithmic scale, so it goes from a few years to hundreds of thousands of years, so it covers a pretty large range. And I plotted the orbital inclination on the y-axis. So low inclinations, meaning planetary orbits would be here. Orbits that are exactly perpendicular to the plane of the solar system would have 90-degree inclination. They would be here, and then everything that's above this plot is a retrograde comet. So now the boundary that was suggested by the International Astronomical Union in 1994 at 200 years to divide the comets into short period and long period is here, and you can see it runs in the middle of this population. Now, if you would forget for a second this boundary, right, and just look at the distribution of the points, You would probably agree that there are two components to this distribution. One is this concentration of orbits at low inclinations and orbital periods about 10 years. This is where Jupiter is, right? Jupiter has the orbital period just over 10 years, so it would be sitting here. So for this reason, this clump of comets is sometimes called the Jupiter family comets, the comets that have some affinity to Jupiter. And then the second component is this dispersed cloud that doesn't show any features. It can have orbital periods as long as 100,000 years. It has some isotropic distribution of inclinations. There doesn't seem to be any preference for low, high, or medium inclinations, right? So for this reason, this boundary that runs in the middle of nowhere is not a very good classification scheme because of comets that have like slightly lower or slightly larger orbital period than the boundary. They are the same. They are not, different. So for this reason, this boundary on classification based on the orbital period is not very useful, not very good. It can serve to, tell the observer, this comet is likely coming back, this one is not coming back, but for a dynamical classification, it's not ideal. The second problem with this classification is that both the orbital period and inclination change over time. As comets have close encounters to planets, both the orbital period and inclination can change, right? So to highlight that, I have taken the classification based on the orbital period, and all the short period comets are red, and all the long period comets are blue. And this is a classification based on today. And I evolved this in the future to see what happens, short time in the future. And what happens is that this boundary is not a barrier to the evolution. And there are some comets that were red, short periodic classified at the present time, but they crossed the boundary on the other side, and there were some long period comets that become short periodic. So that's a second problem with this classification, that the comets are changing their status, and if we would observe, in thousands of years from now, we would classify them differently. So this is not a good base for a classification scheme. So what would be better? And we can do better by using the Tisserand parameter. It was Félix Tisserand who at some point worked as a director of the Paris Observatory. He used it extensively to understand which comets are the same and which comets are different. Basically, the Tisserand parameter is given here. This is a Tisserand parameter given with respect to Jupiter. So this index J indicates Jupiter. So and depends on the semi-major axis of Jupiter. And it's also a function of the semi-major axis, eccentricity, and inclination of the comet. Now, just to remind you what the orbital elements are, the semi-major axis A defines the orbit size. So short period comets will have smaller semi-major axis, and long period comets will have larger semi-major axis. Eccentricity defines the orbit elongation. So, for example, the long period comets will have very large orbital eccentricities, 0.9 or even excess 0.9. And then inclination tells you about the orbital tilt of the comet orbit with respect to the ecliptic plane. So zero inclination would be perfectly in the ecliptic plane, and then larger values indicate larger tilt. And the perihelion distance is a simple function of the semi-major axis and eccentricity. It tells you how close to the sun the comet gets during its revolution around the sun, the closest point. So coming back to the Tisserand parameter, Tisserand parameter is a parameter that is constant, that is preserved during planetary encounters. So here's an example. You have a comet before the encounter. It flies in, it feels the gravity of Jupiter, and is deflected on a new orbit after the encounter. So Félix Tisserand realized, you can have a comet that before the encounter had this orbit, and after the encounter this orbit. These two orbits don't seem to have anything to do with each other, but the beauty of the Tisserand parameter is that they will have the same value of the Tisserand parameter. Semi-major axis change, eccentricity change, inclination change, but the Tisserand parameter is a constant. It doesn't change during planetary encounters. So essentially, each comet is carrying its value of the Tisserand parameter with it, and even if it has encounters to Jupiter, that value doesn't change. This is perhaps a good base for a classification scheme, because we want something that doesn't change, right? And this brings us to a concept called the Tisserand barrier. Let's consider the long period comet, right? It will have a very large semi-major axis, much larger than the semi-major axis of Jupiter, an eccentricity close to 1. That's the reason why these comets are also called near parabolic comet, right? If you plug these two into the expression for the Tisserand parameter, you will see that for whatever inclination of that comet has, the Tisserand parameter is bounded, must be smaller than 2 times square root of 2 times perihelion distance divided by the semi-major axis of Jupiter. It's just simple math, plugging it in, and you get this bound. So this suggests that the comets that start on very large near parabolic orbits will have Tisserand parameter bounded. They will have relatively small values of the Tisserand parameter. So for example, if you have a comet coming closer than 2.5 astronomical unit to the Sun, you can plug it in and you will find that the Tisserand parameter of all these comets will be smaller than 2. The second useful characteristic of the Tisserand parameter is that its relationship to the encounter speed with Jupiter. This is given here. This is the encounter speed of a comet with Jupiter, and it's equal to the orbital speed of Jupiter, about 13 kilometers per second, times square root 3 times minus the Tisserand parameter. So, the comets that are in the Jupiter family, they have low inclinations and they have semi-major axis close to Jupiter. This means that they will have, when they have an encounter to Jupiter, the encounter velocity of the encounter will be relatively low, right? This value will be small, and this indicates the Tisserand parameter will be close to 3 for these comets, larger than 2. And this is the basis of the classification scheme of the comets. We would like to divide the comets in those which have low values of the Tisserand parameter and those which have high values of Tisserand parameter. So this is how it looks on a plot. Perihelion distance on the x-axis, Tisserand parameter on the y-axis. These are forbidden regions. For any combination of the orbital parameters, there are no orbits here. You can't get that combination of perihelion distance and Tisserand parameter in this place or in this place. The Tisserand barrier, the 2 times square root of 2q over aj, is this line here. We know that the Tisserand parameter doesn't change, and therefore the comets that will be here will have high values of Tisserand parameter, and here are distinct and will remain distinct. So I have again color-coded, I have plotted all the comets that we know of and color-coded in red the ones that have Tisserand parameter over the Tisserand barrier and everything else below the Tisserand barrier. And once we do that, we can go back to the original plot, to the orbital period and orbital inclination, and we see that it works beautifully. We base something on a quantity that's conserved, and that gave us a beautiful separation of these red comets sitting in the clump and everything else. So this is a good base for a classification of comets from a dynamical standpoint. And we don't want to use short period, long period, because of that. That has classical definition. So instead, these comets are often called the ecliptic comets to indicate that they have orbits close to the ecliptic. And this cloud is often called isotropic comets to indicate that they can have whatever inclinations, nearly isotropic distribution of inclinations. As a side comment, comet Halley plots here. Before, it was classified as a short periodic comet, so it could have something to do with this clump of short periodic comet. But now we clearly see that based on the dissonant parameter, it is an isotropic comet and is part of this background population. So it's a nice setup for subsequent dynamical studies. Okay, so this was the first part of my talk, and now we switch and start discussing the origin of these two populations. We don't have to invent new things because already back in the 1980s, Julio Fernandez made the following proposal. He proposed that the ecliptic comets are coming from a flat belt beyond the orbit of Neptune, a trans-Neptunian belt, and that's why we have ecliptic comets. And even before, Jan Oort in 1950s proposed that the isotropic comets are coming from this hypothetical cloud, spherical cloud that envelopes the solar system at very large distances, tens of astronomical units away. So at the time that these proposals were made, we didn't know whether the trans-Neptunian belt exists or whether the Oort-cloud exists, and that changed over time because since 1992, there has been lots of discoveries of bodies in the trans-Neptunian belt. We now know about over 3,000 bodies in this belt. So we know for sure that this structure is real, and more than that, we know the detailed dynamical structure. We know that this belt is quite complex, have lots of different populations and stuff like that. So we know for sure that this exists. But for the Oort-cloud, there has been no detection so far. We would need much larger telescope to be able to see the faint objects at these distances, right? So in some sense, this structure is still a theoretical structure and that has been not confirmed through observations. So that's what we have. That's the proposals that we have, that the ecliptic comets are coming from the trans-Neptunian disk and the isotropic comets from the spherical cloud. And what we would like to know now is how in the early solar system you can form the trans-Neptunian belt and how you can form the Oort-cloud, how it happened in the first place, to make sure that we understand things. For that, we need to consider the earliest stages in the solar system. Go back 4.6 billion years and try to understand what kind of effects happen there, right? So last week we were talking about the formation of these objects, formation of 100-kilometer trans-Neptunian object, but also formation of comets. I argued that the streaming instability and gravitational collapse can produce them. And this all happens in a gas disk, in a protoplanetary gas disk, really early on. Now, for the evolution of comets, we don't have to consider these earlier stages when the gas was still around. And the reason for that is when the gas is still around, the kilometer-sized objects are subject to gas drag. So even if they are scattered by a planet outward, they don't go far. They are slowed down and stabilize very close in. So you can't form a trans-Neptunian disk or the Oort-cloud during the gas disk stage just because of the effects of the gas drag. But we have to consider the stages just after the gas went away. Now, the best model we have for the early evolution of the solar system is the NIS model. The NIS model was developed at the NIS Observatory by these 4 scientists. It was published in 3 back-to-back papers in Nature and really opened the field to many different studies. So in the NIS model, the planets, the outer planets, are assumed to be in a compact configuration with Neptune somewhere at maybe 15, maybe 20 AU. This configuration is assumed to result from early migration of the planets in a gas disk that just compacts the system. And then it has been inferred that there was this massive disk of small bodies enveloping the outer planet's orbits The mass of this disk was probably something like 20 Earth masses. That's the best inference we can make about it. Now, as planets scatter these small bodies out, they react to that and their orbits expand. That's something called the radial or planetesimal-driven radial migration of the planet. So Neptune's orbit expands from maybe 20 astronomical units to 30 astronomical units. Then there is a need for, and I will explain that in a second, there is a need for a dynamical instability of the planets, where the planetary orbits are excited to slightly higher eccentricities, and they also are tilted from the orbital plane. And I will come back to it in a second. And then during the late stage, the effects of the background planetesimal disk stabilizes the orbits of the planets where they are now. And at the same time, this massive disk gets dispersed. And we will see that that disk is a source of the reservoirs, of the comet reservoirs. I will show that in detail. It turns out that the best version of the NIS model, the version that works best for the solar system constraints, is the one that has 5 giant planets. In addition to Uranus and Neptune, there is a third ice giant between the orbits of Saturn and Uranus, and this ice giant becomes ejected during the evolution. This is needed to explain the eccentricity inclinations of the outer planet's orbits. And we know from exoplanet studies that young planetary systems are very violent. Ejections happen, and there's plenty of evidence for free-floating planets in the galaxy. So these ejections must be happening quite frequently. So this is an illustration of how what happens during the NIS model with 5 planets. So we can see Neptune interacting with the outer disk, scattering the planetesimals from the inner edge of the disk sphere. We will accelerate a little bit to see what happens. You can see that the planetary orbits expand, and then close to 6 million years, the instability will happen, where this inner ice giant gets scattered by Saturn and Jupiter and becomes ejected from the solar system. At the same time, you see that the outer disk has been dispersed. Planetesimals fly away to large orbital distances. And when we speed up again at 10 million years, just to cover some ground, you will see that the simulation runs over 100 million years. At the end of the simulation, you have very good outer planet orbits. Okay, so there are many reasons for the NIS model to be preferred over other models. I don't have time to describe all these reasons, but I give you at least one. And the one is that the NIS model explains the orbits of the giant planets. So this is a comparison between the real orbits of the planets, which are these triangles. You have the eccentricity on the left and inclination on the right. The x-axis plots the semi-major axis of planets. The planets are color-coded: red for Jupiter, green for Saturn, turquoise for Uranus, and blue for Neptune. So as I said, the triangles are the mean eccentricities of the giant planets, or mean inclinations of the giant planets. Now the evolution of the system during the instability is stochastic, right? So it's not enough to do just one simulation, because you will get some random result from it. The thing you can do is to run a large ensemble of simulations, see what the results are statistically, and then statistically compare that to the real solar system. So in this case, we ran 100 simulations, collecting those where 4 planets survived, and the dots here are the results of these simulations. So as you can see, there is quite a bit of spread, and that's the result of the instability. You can't control that. Sometimes you get lower eccentricity, sometimes higher. But there is also a good overlap between the points and the real orbits, indicating that the NIS model works quite well to explain this mild excitation of the giant planets. If there wouldn't be any instability, and the planets would just migrate into that outer disk, they would end up with eccentricities exactly 0 and inclinations exactly 0. So there is a need for the instability to explain these mild eccentricity inclination of the giant planets. Okay, so now let's forget about the planets and let's care about the small bodies. What do the small bodies do in the early solar system? And this is a situation just shortly after the instability, where the outer disk is being scattered out. The inner ice giant had been already ejected. And what I will do is I will tilt the plane so that we see the population edge on, right? And then I will zoom out so that we see what happens on a much larger scale. So this is the view. You have now million astronomical units on the x-axis. So what you are looking in is not actually the solar system. This is more like the sun's stellar neighborhood. Alpha Centauri would be somewhere here if I would plot it, right? And the point here is that at this point, early on, there is no spherical structure. There is no Oort-cloud. Bodies have been scattered along the ecliptic, sometimes to extremely large distances, where already unbound from the sun and will become part of the galaxy. But at this point, the scattering produced by the giant planets basically scattered everything in the same plane to very large distances. And now let's see what happens when we put this in the n-body integrator and simulate it over time. That integration have to account for additional effects. And the additional effects are the gravitational field of the galaxy, that at this time scale starts to be important, and also the stars that can fly through this cloud at some point and can mix the cloud as well. So both these effects are included in this simulation. So this is what happens. So you can see that there have been quite many changes in the distribution. I will, this is around to 500 million years, but I skip all the way to the present time. The simulation run over the whole age of the solar system. So this is the initial situation where we have this flat disk with the wings. These are unbound objects that will be removed. And this is the final situation at the present day. And there has been a huge change, and we can see that indeed there is a spherical structure, you know, a few tens of thousands of AU across that just formed from in the simulation, right? And that's the effect of the tidal field of the galaxy. Now, we would like to understand how this happens. Why is it that, you know, this structure evolves into more spherical? How the inclination change, because of here you have still relatively low inclination with respect to the ecliptic, and here the inclinations are pretty substantial now. So for that, as always, it's good to look in the orbital elements. So here you have the same major axis and inclination with respect to the ecliptic. It will be the same simulations we have seen before, but now showing the orbital elements. Again, you have the logarithmic axis, logarithmic scale on the x-axis to see what's happened at very large distances from the sun. And this block here of points is the initial belt, initial trans-Neptunian belt of bodies that was put there in the NIS model. So this is the kind of evolution you get from it. Again, I will not let it run all the way to the present. That would take some time, and I'll skip to the present. So what happens here that we had this initial disk, but that disk was scattered by the giant planets outward. The bodies that were scattered to tens to hundreds of AU remain on relatively low inclinations, and that is a flat trans-Neptunian disk that's actually observed, right? But then, if the bodies are scattered beyond 1000 AU, something else happens. And the inclination don't stay low anymore. In fact, they increase substantially with a very large population that becomes retrograde. And that's the effect of the galactic tide. But let's ask the question, how the galactic tide does it? What is the galactic tide, in fact, and how it increases the inclinations? For that, we have to consider the gravitational field of the galaxy. We don't care what is happening on the other side of the galaxy. We don't care what's happening close to the nucleus. We only care what's happening in the solar neighborhood, right? Because of the comets remain in the solar neighborhood. And in that case, in the simplest approximation, the gravitational field of the galaxy can be approximated by this equation. Now we are working in the galactic coordinates. So the z vector points to the north galactic pole, and we consider the galactic plane. This might be at some point a little bit confusing because of the comets, when they are scattered to large distances, they are subject to effects from the solar system, where the ecliptic plane is the reference. But when they are at very large distances, they are affected by external perturbations. So the galactic plane is the reference. And people who study comets often have to switch between the two coordinate systems. So this force is, first of all, oriented perpendicular to the galactic plane, right? And it points towards the galactic plane and has a magnitude that's proportional to the distance between the comet and the galactic plane. So this force basically is larger when the comet is far from the galactic plane and smaller than when it comes closer to the galactic plane, and when it's under the galactic plane, it's pointed up. So it's a relatively simple force. Now, what are the properties expected from this evolution? So first of all, this vertical force doesn't change the orbital energy. This means that comets subject to that force will have the same orbital energy, which links to the semi-major axis. So the galactic tide doesn't change semi-major axis of the comet. It cannot expand it, cannot shrink it. The semi-major axis will always stay the same. The second thing, because of this toroidal symmetry, the fact that the galactic tide is a vertical force, it will preserve the z component in galactic plane, z component of the angular momentum, orbital angular momentum of the comet. And this is the z component. It is written as a function of the orbital elements, semi-major axis eccentricity. But as I said, now we consider the inclination with respect to the galactic plane. So when the comets are scattered along the ecliptic, they will have low inclination with respect to the ecliptic plane, but because of the ecliptic plane is inclined 60 degrees to the galactic plane, they will immediately have 60-degree inclination in the galactic plane. But the important thing is that this quantity is conserved. This is constant, this is constant, this is constant. So if this is conserved, that means there will be a relationship between the eccentricity inclination. The galactic potential will be capable of changing both the eccentricity and inclination, but have to do it in a way that this quantity is conserved. And that brings a relationship between the eccentricity and inclination with respect to the galactic plane. For example, if the comet is scattered, has some initial eccentricity inclination, say it's scattered by Neptune, so it has perihelion distance 30 AU, so it's scattered out, then the galactic plane perhaps can increase the inclination. Why not, right? Can increase the inclination. This will increase, and therefore the eccentricity will decrease. When the eccentricity decreases for a fixed semi-major axis, then the perihelion will increase. And the comet that had perihelion at 30 AU will have suddenly perihelion at 50 AU, then 100 AU, maybe 1000 AU. What happens during this evolution is that the comet decouples from the outer planets and reaches a more stable orbit where it can live without being perturbed by the planets. No danger of ejection or something. It's just stored in a reservoir. And that's basically why we have the Oort-cloud. Comets scattered along the ecliptic become decoupled, inclination increase, change, and we generate the spherical Oort-cloud. So this is an example of that evolution. This is again in galactic coordinates. So say this was a comet that was ejected by Neptune. So it comes very close, comes to 30 AU to the sun. And it has a modest inclination in the galactic coordinates. Then over time, the galactic tide will change it like this. Inclination will increase, eccentricity will decrease, so it decouples from the system, and it evolves like this. Okay? So these are the stages. So at this point, it should be more or less clear why the Oort-cloud forms, is the effect of galactic tide. Now, how it happens that comets come back from the Oort-cloud? They are stored there for billions of years. How do they manage to come back? And the answer to that is simple. The galactic tide always exists. It will be there. So over time, the comet that evolved into the Oort-cloud, it can come back and become a comet. So the galactic tide is both responsible for creating the Oort-cloud and also responsible for bringing the comets that were stored in the Oort-cloud back into the inner solar system. This is a small illustration of it. What I've done is that from these giant simulations that we have with millions of comets, I've taken just one. This is an Oort-cloud object. This is for scale, so maybe the semi-major axis is something like 10,000 AU. It's well decoupled from the system. Maybe the perihelion is 5,000 AU. So this is an Oort-cloud. It has large inclination in galactic coordinates. It's almost perpendicular. So this is an Oort-cloud object. And this is what happens over time as I just follow this object and plotted the orbit over time. So you can see the effect of the galactic tide. The orbit becomes less inclined, more eccentric. The semi-major axis is roughly conserved, but you can see some jitter there. This is because of the encounters of that body to the giant planets. So this basically illustrates how an Oort-cloud object becomes a comet now, and then if it survives, doesn't physically disrupt or is not scattered too much by the giant planets, it just cycles back to the Oort-cloud. So the closest approach in this case is only at 15 AU, so this doesn't become a real comet. Comet needs to evolve closer in, and that's also the reason why this object survived the perihelion passage. Okay, so based on all this, we have basic understanding how this evolution happens. So early on, we have the trans-Neptunian disk that's scattered out on a time scale of something like of tens of millions of years. It's scattered to very large distances where the galactic tide starts acting on that, rises the inclination, sometimes to even retrograde with respect to the ecliptic plane. Then the body is stored there for up to 4.6 billion years. And then, just by chance, evolves back by the effects of the tides, and then it gets scattered by the planets again and arrives on a cometary orbit that has very large semi-major axis and very large inclination, becomes an isotropic comet. The ecliptic comets have a much simpler life. They are scattered just by chance to lower semi-major axis. They don't never reach to these distances. And therefore, there's nothing that can increase their inclination. They stay close to the ecliptic. So they cycle into the trans-Neptunian region. They are stored there for 4 billion years. And then randomly, by chance, some of these objects come back to become the ecliptic comet. So that's the basic difference between the life cycle of isotropic comets that evolve to very large distances and ecliptic comets that do not. Now, from the simulations that we have, we can ask, like, where Julio Fernandez and Jan Oort correct when they proposed that the ecliptic comet are coming from the trans-Neptunian region and the isotropic comet are coming from the Oort-cloud. And yes, the answer is yes, they were right. We can look in the simulations that we have and plot the original orbits of, I subsample it to 100 comets to give you the percentage. You can clearly see what the percentages are. What the original orbits of isotropic comets are. We have the simulation produces the isotropic comet, so just like the isotropic comet, go back and see from where it evolved. And then I do it for 100 bodies to plot it here. So as you can see, the Oort-cloud indeed makes most of the isotropic comets. 97% of isotropic comets are indeed coming from the Oort-cloud. There are 3 exceptions. The ecliptic comets, on the other hand, are produced by the trans-Neptunian disk. There are some comets that evolve to the Oort-cloud and can mimic the behavior of the ecliptic comets, but that pollution is of the order of 10% only. So it's not a big deal, but it's an interesting fact that some in the population of the ecliptic comets, perhaps 10% of those should be the ones that spend quite a bit of time in the Oort-cloud. Now we can ask more specific questions, right? We have this modeling, and we can ask, for example, if in the model that produces the Oort-cloud and produces the isotropic comets later, if it produces the right distribution when compared to observations, right? So let's start with the isotropic comets. This is the semi-major axis distribution of isotropic comets. And it's very interesting. It's, in a sense, bimodal, showing a broad peak at low semi-major axis below 10,000 AU, and sharper peak at larger semi-major axis. So what is this? This peak, in fact, are the comets that are evolving from the Oort-cloud, but they had already a perihelion passage before the second one that we see. I didn't say it too well, but what it means is that if you take any comet in this population and integrate it backwards, you will see that that comet, in addition to the perihelion passage that it's having now, had another perihelion passage maybe 100 million years ago. So these are comets that have been in the Oort-cloud. They had at least one perihelion passage before they were seen, and now they are coming maybe for the second, maybe for the third time back, and they're seen. So that's why this peak is called the peak of the returning isotropic comets. These, on the other hand, when you integrate them backwards, you clearly see that they didn't have any perihelion. They are coming to the inner solar system for the first time since their ejections in the inner solar system. So that's why these comets are called the new comets, and this peak is often called the Oort peak. These are comets coming from the Oort-cloud distances. Now, so does the model reproduce this or not? And for the dynamical model to be able to reproduce this, we need to account for comet disruptions. Comet disruptions are happening all the time. We don't know exactly why they are happening. Maybe there is a variety of reasons. It could be some catastrophic sublimation event. It could be a rotational spin-up and rotational fission. It can even be small impact. But comet disruptions are seen all the time, and this is an observation of one of these disruption events when Comet Atlas has been split in many different fragments. So to account for the physical disruption of the isotropic comet so that we can fit the observations, account for that physical effect, usually we assume the simplest possible disruption law that goes all the way to Whipple. The disruption law is simply probability is surviving to the third or to the fourth perihelion passage as a function of the perihelion passages below 2.5 AU. So for example, while surviving to the first perihelion passage, that's 1. Surviving to the second perihelion passage is 65%.
This is the functional form that Whipple assumed. It's a simple power law. When n is the number of passages and kappa is a free parameter. We don't know what the kappa is, and it's something that has to be fit to the observations. And this is an example for kappa is 0.6. So in this case, a comet has 50% probability to survive to the third perihelion passage. So in this setup, the comet disruption happen all the time, right? So this is the result when we combine the dynamical model with this physical effect and adjust kappa so that the fit is good. So you have the observations with the error bars, and this is how the model reproduces it. It's not ideal, right? It's run a little bit higher here, a little bit to the left here, but overall, it's a pretty good correspondence. The model reproduces the Oort peak and also have the returning comets. Now, this happens for the best value of kappa, about 0.8. If kappa would be larger, then comets would be surviving less. And then the model indicates that the Oort peak would be much larger and there wouldn't be too many returning comets. So if, on the other hand, kappa would be small, then the comets would be surviving a lot. We would have small peak here of the new comets and then a huge peak of the returning comets. So that's how the kappa is adjusted to reproduce the observations. And the same model, although I don't show it here, the same model also reproduces the isotropic inclination of the observed comets. That's because of the cloud is pretty much spherical, and also reproduces the distribution in the perihelion distance of the isotropic comets. So it looks pretty good. So this was for the isotropic comets. Now let's go to the ecliptic comet population. This is the observed population of active ecliptic comets. So you have the semi-major axis distribution here, inclination distribution here, perihelion distance distribution, and the Tisserand parameter distribution here. So, for example, if you look at this cumulative distribution and inclination, you can see that the median of the distribution is about 13 degrees. For comparison, the isotropic comets have median 90 degrees, right? So that's the flatness of this population. And now if we account for the physical effect and use the dynamical model that we developed, we can try to see how it works. And it works very beautifully. The black line is the model distribution. There are many more comets, so it's much smoother than the observations, but there is a great fit to the observation. An interesting consequence of this fitting that also here we have to adjust the physical lifetime of comets, like we did for the isotropic ones. But here it's different. The isotropic comets were surviving only 1, 2, maybe 3 perihelion passages, but to obtain this fit, we need that the ecliptic comets survive hundreds of perihelion passages, right? If we would impose just a few perihelion passages, then the inclination distribution would be just wrong. So what's happening here, it's not very clear. For some reason, the isotropic comets are more susceptible to disruption than the ecliptic comets. Maybe they are a different kind, maybe they are smaller, and therefore they disrupt more often. Maybe because they were stored at very large distance and coming back, they experience a very large thermal gradient and are more active. That's actually observed, that the long period comets or the isotropic comets are typically more active and therefore can disrupt more often. But this is a subject of investigations, and people are studying this, what could be causing this difference between the physical lifetime of ecliptic and long period comets. So these are some of the key points to remember from this lecture. There are 2 dynamical classes of comets. Ecliptic comets have short orbital periods and low inclination. Isotropic comets have long orbital periods and large inclinations. And we use the Tisserand parameter to distinguish between these two comet types. In the early solar system, the giant planets scattered small bodies to distances larger than 1000 AU. They were affected by the galactic tide and stored in the spherical structure that we call the Oort-cloud. The bodies that were scattered only to 30 to 200 astronomical units, not all the way to those large distances, remained in a flat trans-Neptunian disk that is characterized now from observations. The Oort-cloud is the source of present-day isotropic comet population, and the trans-Neptunian disk is the source of ecliptic comets. That's what we discussed. This was a lecture for today, talking about comets and their source reservoirs. The next week, we will move a little bit closer to the sun, to the inner solar system. And I would like to discuss these giant collisions that happen between asteroids that are capable of disrupting 100-kilometer bodies in small pieces. I will explain how these pieces can be traced back to the same collisions and are identified as collision families. And I will also talk about the potential relationship of some of these families to meteorites that we collect on the Earth. And that's all for today. Thanks for coming, and I hope to see you next week.